All right, good morning, Sensei. This is Mr. Spensei, and we're actually going to run a two-sample hypothesis test and two-sample confidence interval. Video may take a little bit longer, and the reason being is we've got to break down the recipe cards for each one of them. So first off, our null hypothesis. We have two separate groups, so we're going to say mu1 equals mu2. That's my preferred way just because it's simple. But you could also do mu1 minus mu2 equals 0. For the alternative, mu1 greater than mu2, mu1 less than mu2, or mu1 greater than mu2. And once again, if you prefer, you can do mu1 minus mu2 does not equal 0. mu1 minus mu2 is greater than 0. Or mu1 minus mu2 is less than 0. Again, all of those are equivalent, completely acceptable. It's up to your choice. I just do this one because it's easy, but it's up to you. If you want to include the 0 and that helps you out, that's great. Once again, we have to define the parameter in context, and we have to write our conditions. So both samples are random, and we also have to address independence. In this case, we don't have, the differences aren't independent, but the samples are independent. And this might help you keeping that straight. When to use independence. If you have two sets that are measured, whether it's something measured twice, or if we are having two separate groups, we have to have independence. In this case, we have to have independence. Once again, N has to be less than 10% of the population. In other words, we're trying to say that even though we're sampling without replacement, it does not impact, they're close to being independent. And we have to have a normal population. This is our normality condition, or N is greater than 30, or we're going to have to draw a box plot. Now, the facts of the matter is we're going to have to do this since we have a mu1, we'll have to do it for that group, and we'll have to do it for this group as well. We'll have to do it for both. The next thing it says, write the equation. Well, I'm going to go back to what we've had before. What we had before is our equation looked more like this. X bar minus mu minus, or X bar minus mu over S divided by the square root of N. Well, here we're changing that up a bit. You're probably wondering where the mu's go. So, and it's actually this right here is a shortcut for that. And so we have a lot of things I want to talk about. We have T equals X bar 1 minus X bar 2, and that probably makes sense. It also really, technically, this also exists. You also have that. But what was our null hypothesis? Our null hypothesis is that equals 0. So since it equals 0, we don't bother writing it down. Now here we have S divided by the square root of N. Well, we have that for 1, and then we also have it for the other. So now I'm trying to add standard deviations of X bar. Well, we can't add standard deviations directly. We have to square them and take the square root of them. Well, if I square them, this becomes S1 squared over N1. This becomes S2 squared over N2. And then we take the square root of it. So that's where that part of the formula came from. It's because you can't add standard deviations first. You have to square them before you do so. All right. After that, everything else runs exactly the same. And I could read it off to you, but it just makes things a bit longer. And I don't think you want to do that because we'll be referring to it as we are working our first problem. So our first scenario. The average ACT score of an independent random sample of 16 non-athletes at Blinn College. So we have non-athletes and we have 16 of them. Random sample at Blinn College was compared to that of an independent random sample of 7 athletes. All right. The school's guidance counselor was curious to know whether or not Blinn was admitting athletes with lower ACT scores than non-athletes. So we wanted to know whether the athletes have a lower, so non-athletes being greater than athletes. So here's my parameter definition. Let mu1 equal a true population mean ACT score for non-athletes, and we think that they are greater than athletes. And let mu2 equal a true population mean ACT score for athletes. So my null hypothesis is that mu1 equals mu2, that there's no difference in ACT scores. And here we're saying that the ACT scores of the non-athletes are greater than the athletes. Well, condition. We have our non-athlete conditions, which are random samples given. Samples independent, great. 16 divided by 0.1 or 16 times 10, there's 160 athletes at blend. All right. We'll check the box plot in just a moment. Then we have a random sample of athletes. That's good. Sample is independent of the other sample. That's great. And then a 7 divided by 0.1, which is 70, or 70 times 10. Reasonable to assume that there are at least 70 students who are not athletes. Who are athletes. There are more than 70 athletes at blend. All right, and again, we need to check the box plot. Why did we need to check the box plot? Well, we need our normality condition, and our sample sizes were not 30 or larger. If they've been 30 or larger, we'd be good to go, but they're not. So I've gone to stat edit, and I've entered the data into L1 and L2. I put the non-athletes in L1 and the athletes in L2. Go to your Y equal, make sure there's nothing turned on in Y equals, and you might even need to scroll all the way down, because that sometimes is the errors that we run into when we're running these things. Second quit. Now we're going to go to second stat plot. And in this particular case, I'm going to go ahead, I can go second stat plot again, and I'm going to turn off my second one. And now I only have one stat plot on, so I can see one at a time. I'm going to go stat, second stat plot, enter, make sure that's on. Arrow over, select a box plot that I want, which is the one showing outliers, and press enter. Then my X list is an L1, second one. And I press zoom 9, and I get one. Problem with this is it's really nice to have both of them stacked together. So there's my first one. So if I go back to second stat plot, I can go up and turn this one on as well. Choose the box plot showing the outliers. Press enter. Then I'm going to drop down and choose my X list with second 2. Once again, zoom 9. And now I have both. All right. So now I have both of them, and I can use the trace feature to get the most important points. When I look at either one of these, they both are definitely no outliers, and they're somewhat symmetric or reasonably symmetric, and it'd be okay to proceed. And we notice that the median of the athletes is below the median of the non-athletes. Now I can get the data for the test in a couple different ways. I'm going to go the long way first, just so you don't forget about it. I can go stat calc one variable statistics, and I can go to L1, and my X bar 1, these are the non-athletes, is 24.75. My standard deviation for the non-athletes is 2.84. I had a sample size 16. And if I want to, I can get all my box plot information there. I can also go to stat calc one var stats and change it to second 2. And there's my 7 athletes that I input with a mean of 21.8, standard deviation is 3.28. And once again, I can scroll down and get all my box plot information. So that's one way. I tend to just go straight to the end and go stat test. And I'm going to scroll down to 2 sample t-test, which happens to be number 4. I have data, and my data happens to be in L1, second 1, and my other list is in L2, second 2. My hypothesis had a greater than, so I need to make sure that I have a greater than. And then it asks whether we want to pool. Well, the nice thing is when we're working with means, we will never pool. We'll never be required to. So we can press calculate and press enter. All right. And so we end up getting all of our information. There's our sample mean for the non-athletes, sample mean for the athletes, sample standard deviations for the non-athletes, sample standard deviations for the athletes. And so I just plugged them into the equation. Sample mean, non-athletes, sample mean, athletes, etc. All right, run that real quickly since I accidentally cleared it. And we ended up getting a T statistic. It's really important that you write this down. And the probability of the T statistic is 2.021. And here's what we're saying. We're saying the claim is that there's no difference between athletes. We wanted to check to see if non-athletes were greater than, so we're going this way. We ended up getting a T statistic of 2.021. Our actual mean, the actual claim mean was 0. And we ended up, I actually don't even know what we got, but it really doesn't matter. This is our T value. And we ended up with an area of 0.0352. We checked this at an alpha of 0.05. So 0.0352 is less than alpha of 0.05. Since it's less, we reject the null. So here's the way you write it up. Our p-value is 0.0352. We reject the null. There is sufficient evidence at alpha equal 0.05 to suggest that the difference in the true population mean of ACT scores for non-athletes is greater than that of athletes. All right. And basically, true population mean of ACT scores for non-athletes is greater than that of athletes. On average, this is a single, making it explainable to the poorly educated. Non-athletes is greater than that of the athletes. All right. So that takes care of that. We're going to look at the confidence interval. We'll probably get through that a little bit faster. So the confidence interval. We still have to define our parameters in context. We still have to write our conditions. Our conditions are the same as on the other page. Our formula is, well, our basic T formula was X bar plus or minus T star S divided by the square root of N. Here, we have two standard deviations, and it's just like I discussed on the other page or in the other part of this video, we have to square them and convert them to variances first. All right. We don't worry about the means because the means are assumed to be 0. All right, so here we go. Everything is the same, except we need to look at the degrees of freedom. You will need to write this down, but those degrees of freedom actually come from the calculator. It's a very long formula, but College Board doesn't make us learn it. So since they don't, we can just use the one that came from the calculator. All right. And there we go. Everything else is pretty much the same. So let's take a look at this. First off, I'm not going to reread this because it's the same thing, but they're asking us to do a 95% confidence interval. So mu1 equals the true population mean ACT scores for non-athletes. mu2 equals true population mean ACT scores at Blinn College, for athletes at Blinn College. We don't have to write the null in the alternative. Sometimes it's helpful, so I did. I'm not going to restate the conditions. We did that on page 195, so make sure you are on the previous part of this video, so I'm not going to redo that. And here we end up with our equation, and I need to plug in. Well, the way I do that is I go ahead and run the test. So stat test, we're going to scroll way down to 2 sample T interval, which happens to be 0. I think that's like 10. Press enter. We have data. and it's 0.95. And like previously, we're not going to pool. I'm going to go ahead and run the test. So we end up getting, this is our interval, negative 2.907 to 6.0765. And we have degrees of freedom of 10.12. We have our sample mean for our athletes, our sample mean for our non-athletes, standard deviation for athletes, non-athletes, sample standard deviation for non-athletes. I'm saying that completely wrong. This is our sample mean for non-athletes. This is our sample mean for athletes. This is our standard deviation for non-athletes. This is our standard deviation for non-athletes. And there are our associated sample sizes. So we need all that information down, and it's going to be really important that you get those degrees of freedom from this part right here, 10.12, because you'll need those. When we go to plug into our formula, we have our X bar 1, we have our X bar 2, we have our standard deviation for our non-athletes, and we have our standard deviation for non-athletes, standard deviations for athletes, but what we're missing is T star. So the question is, how do you get that? Well, we're going to, like you thought, we might go back to second bars inverse T, parenthesis 1 minus 0.95 divided by 2, and our degrees of freedom are 10.12. And we end up getting 2.22. All right, so that's where the 2.22 came from. So in this case, we are 95% confident the true population differences in the means of ACT scores between non-athletes and athletes at Blinn College lies within this interval. If we did this over and over again, we'd expect that this method would capture the true population difference in ACT scores between athletes and non-athletes at Blinn College 95% of the time. We should note, if they ask us, is there a difference? 0 lies within the interval. Therefore, we are unable to determine at the 95% confidence level whether or not athletes or non-athletes have higher overall ACT scores. The last thing is, they ask, is the 95% confidence interval consistent with your hypothesis test? Well, on the previous part of this video, we rejected. We said our p-value was less than alpha. So we said our p-value was less than alpha, so we rejected, but here we can't make a decision because 0 is contained. So the hypothesis test is not consistent with the confidence interval. The hypothesis test found the ACT scores of non-athletes was higher than that of athletes, while the confidence interval could not determine a difference. Why did this happen? And the reason it happened was the hypothesis test was one tail, and the confidence interval is two tails. When you go from one tail to two tail, you have to double your p-value, right? You have to, when you go from one tail to two tail, you must double your p-value. And that is why they were not consistent, although they both basically look like 95%, all right? Okay, oh, and had we run this as a, had we run the previous hypothesis test as a two-tail test? The answer. All right, thank you for watching.